Okay, so we are now going to talk about ways in which we can get hold of a complete orthonormal basis, because that's a basis that we can use for the completeness relation. And to do this, it's very natural to speak a little bit about Hermitian operators. So let's consider a Hermitian operator. And the specific operator that I'm going to consider in our two-dimensional Hilbert space is just given by 0, 1, 1, 0. To say it's Hermitian, I mean that A is equal to A transpose. If I was working in a complex vector space, I would say that A is equal to A dagger, which means that A is equal to A complex conjugate transpose. Now, why do we look at Hermitian operators? Well, there's a few important properties of Hermitian operators important for us. So first of all, we are assured that we can solve the eigenvalue problem of these operators, and we can find the eigenvectors. So that's the first guarantee that we have for a Hermitian operator, that we can actually find the eigenvectors. The next thing that we know is that the eigenvalues are real. And the last point, and this is really the point that is most important for us, is that the normalized eigenvectors provide an orthonormal basis. And that's what we're interested in, finding an orthonormal basis. So for this operator A, I'm going to solve the eigenvalue problem. I'm going to work out the eigenvectors, and then I'm going to check the completeness relation. So let's call the eigenvalues of A, there'll be two of them, because it's a 2 by 2 matrix. Let's call them lambda 1 and lambda 2. Now, what we know is the trace of A will be the sum of the eigenvalues. And just looking at A there, the trace of A is 0. So we know the eigenvalue sum to 0. The determinant of A is the product of the eigenvalues. The determinant of A is -1. Well, this is a trivial pair of equations to solve. We learned that lambda 1 is equal to 1, and that lambda 2 is equal to -1. Given the eigenvalues, we would like to determine the eigenvectors. Now, this is a very simple standard exercise, so I'm just going to write down what is the solution. Well, the eigenvector for the eigenvalue +1, so notice I'm again labeling the eigenvectors by the value of the eigenvalue. That's what it's given by. And to really check that I didn't make a mistake, you should check that operator A acting on the eigenvector is equal to the eigenvalue times the eigenvector. And similarly, the eigenvector with eigenvalue -1 is given by 1 over root 2, 1 minus 1. And I have normalized both eigenvectors, and this is the equation that you would use to check that I didn't make a mistake in writing down that second eigenvector. Okay, so remember the schematic form of our completeness relation. It said sum over a complete basis of ket vector, bra vector, that is 1, the unit operator, and for us, the sum over the complete basis would be +1 plus 1, plus, minus 1, minus 1. And what does that equal to? Well, if we take the plus 1 times the plus 1 over root 2 times 1 over root 2 is 1 over 2. And then we have 1, 1. So ket plus 1 into bra plus 1 plus, now let's come to the minus 1 eigenvectors. 1 over root 2 times 1 over root 2 is 1 over 2. Then we have 1 minus 1 and 1 minus 1. What does that equal to? 1 over 2. If we multiply this out, well, that's just some simple matrix algebra. So I'm going to leave you to do that. Make sure I didn't make a mistake. And if we now add the two terms, the off-diagonal terms sum to 0, and the diagonal terms sum to 1. So that's lovely. Indeed, we did get the completeness relation holds. So the point is, when we look at this relation that we wanted to understand, we now know geometrically what does this relation mean. It's just projecting, if you act on a vector, the statement is the vector is just being projected into components and summed. And we know we have a complete basis because, in fact, ket k is an eigenket of the momentum operator. There's just two more comments that I want to make. The first one is that I saw some of you saying in your solutions that the completeness relation has something to do with the conservation of probability. Now, that's not true. You know, we've derived the completeness relation using the fact, or we've derived the completeness relation as a property of an orthonormal basis. We haven't anywhere said anything about whether this basis, whether the wave function was normalized or not. And in fact, we haven't even spoken about state, a wave function. So the fact that the sum of probabilities is equal to 1, let's see how you get that statement. In fact, that's the statement that the norm of psi is 1. This is the statement that the sum of probabilities is 1. So let's maybe write it out in a way that will further convince you. So first of all, what I want to remind you is, if you take k onto psi, well, this is what we would mean by psi of k, the wave function in momentum space. And if I take a dagger of this equation, okay, so if I dagger it, well, ket psi will turn into bra psi, bra k will turn into ket k. So that's the result of taking the dagger. And on a normal function, all that dagger does, it takes a complex conjugate of the function. So those are the two relations that we have, okay? This first relation, you can think about, it's a definition of what we mean by the wave function in momentum space. The second relation followed by daggering. Now, let's say 1 is equal to psi psi. Now, this can also be written as psi. And now I'm just going to sandwich a 1 in the middle. And of course, because this is just the identity operator acting on psi is still just psi. So I just used the completeness relation here. Psi itself does not depend on k, so I can write the integral d3k outside. Then I have psi k and k psi. And these two brackets appearing in the integrand, I've already evaluated. So this is just the integral d3k. Psi k is nothing but psi star of k, and k psi is nothing but psi of k. So this is equal to the integral d3k of the mod of psi of k squared. And this is maybe a more familiar way that you've seen to say that the probabilities sum to 1, but you can see this is equivalent to our original equation, which told us that psi is normalized. So that's the statement that the sum of the probabilities is 1. Okay, very last point. So let's consider the following. Let's start with psi in position space. And I'm again going to apply the completeness relation. So I've got bra x, then I've got an integral d3k of k psi. And x doesn't depend on k, so I can pull the d3k integral outside. We've got a k, and then we've got k psi. Now we know what k psi is. That's just psi of k by definition. So this is an integral d3k. This is psi of k. And now I want to remind you, this overlap of the momentum eigenstate in position space, we use that in our calculations in this chapter. This is equal to 1 over 2 pi to the 3 over 2. Remember, we've set h bar to 1. And then we've got e to the I k dot x. So plugging that in here, we've got 2 pi to the 3 over 2, e to the I k dot x. So one of the things that the completeness relation allows us to derive is that psi of x is equal to the integral d3k over 2 pi to the 3 over 2 e to the I k dot x psi of k. And this last equation that we've written down is nothing but the Fourier transform. Okay, so why don't you see if you can derive the inverse Fourier transform? And the last point that I want to make is this is how the completeness relation is used perhaps most often. It's used to change basis. Here we use the completeness relation to change from the position basis. So we started in the position basis, and we use the completeness relation to change to the momentum basis. So the completeness relation allowed us to derive the equation relating the wave function in momentum space with the wave function in position space.